Okay, so the recording is started, and Francesco, you can go ahead. Thank you.
Okay, so good morning. Today is a is a pleasure for me to have at the TMS as speaker Dr. Lulu from the University of Wisconsin Madison in the United States. So just to introduce you a bit about Lou. She's I know her because she was a PhD in the Biology Observatory experiment where I work actually. So on and she worked on for the Biology Observatory on the detection of very high energy cosmic ray shower with the surface detector, and also on the detection of the search for photons at the highest energies. She did the PhD between the University of Leeds with Alan Watson, that is one of the very important person in our field, and also in Wuppertal, where there is also another important group that is a part of Auger. And after the PhD, she went to Chiba University in Japan as a postdoc, where she started to work with the IceCube Neutrino telescope experiment. That is the experiment searching for neutrinos, very high energy neutrinos, and is the one that she will introduce us. Is an experiment that is in Antarctica, but I don't want to spoil the talk by Lou. So I think it's enough. The rest Lou will say to us in the next 40 minutes. Thank you.
Thank you so much for the kind invitation and the introduction. So could you see the slide?
Yes.
Okay. So yeah, thanks again for the kind invitation. So I'm going to talk about this experiment in South Pole. It's called IceCube Neutrino Observatory. So before we go to neutrino, I will invite you to think about what is color. So in school, you have prism, and you use the sun to shine at it, and you see a rainbow of colors coming out. So the colors actually they actually correspond to different wavelengths of photons. So this is acceptance of human eye, for instance, and this is acceptance of CCD camera. So the visible colors, different colors, actually corresponding to about 500 to 600 nanometers, for instance. So these are photons. So the visible photons, so they only occupy a very short range of the wavelengths or the energy band of the electromagnetic waves. So if you go to this larger wavelengths, then you have radio waves, and all the way as you go to higher energies, you have infrared. So here is the visible, you have UV, X-ray, and gamma rays. So we're quite familiar with these photons because they're everywhere in our world. We use it for radio, we use it for GPS, microwave, for instance. We also use photons. Oh, this is Hawk because he was essentially turned to Hawk because of gamma rays. So we use photons actually in our study of the universe since very early on. So this was just a recording of a supernova about more than 1,000 years ago. So this was observed by our eyes. You might be able to read it if you read Chinese. So this is Galileo's first telescope in 1609. So that was optical. So today, with the advancement of technology, we are able to fly into above our hemisphere, and you see we have the gamma ray detections, actually the satellites, X-rays, and we also have ground-based optical detectors and radio detectors, etc. So our understanding of our universe has been advanced quite a lot in the last century. So this is just an example of multi-wavelength Milky Way. So Milky Way is our home galaxy, and you can see it in different wavelengths of photons. So you're more familiar with optical here. And so this is near infrared. So this is the highest energy gamma ray. So you can look at our own home with different wavelengths of photons and then understand what's going on inside the galaxy. So this is pretty cool. So what is neutrino? So far we've talked about photons. So you see this is x-axis is energy, microwave, infrared, optical, X-ray, gamma rays. That's what we talked about. So that's all good. Y-axis is distance, how far these particles can travel. So for X-rays, for instance, we can measure the photons pretty much from very far away distance, like the edge of the universe to us. But as you go to higher energy, when you want to study the highest energy phenomena in the universe, these photons we interact with our cosmic microwave background, so where the pair production, so gamma pair production. So when you go to PeV, so 10 to the 15 electron volts, the gamma rays, the photons, can only travel as far as our galactic center. So you can only study the high energy phenomena up to our galaxy. You can't see beyond. So this is where the particles came from. So this is at this highest energies, we would like to use neutrinos or cosmic rays to study these highest energy particles, because the universe is still transparent to neutrinos. They're weakly interactive. So this is just illustration of astroparticle physics. This is what we do. We try to study the smallest particles. So here weak interactions, W boson, at this huge universe scale. That's just because universe is able to produce its highest energy particles at energy much beyond what human can do with, for instance, Large Hadron Collider. So you're more familiar with atoms. You know the scale is about 10 to minus 10 meter, and what we're doing is essentially going to much smaller scale down to almost 10 to the minus 18 meter. So at this smallest scale, these particles yet carry enormous amount of energy. So this is what we're interested in. We want to probe these most extreme energies at these very small particles to understand how does universe actually accelerate these particles, and also can we find some physics that is beyond standard model. So this is something super exciting in this field. So just a brief overview, just a review of the standard model. I believe a lot of you know already. So we have 4 types of fundamental forces. So for photons, this is in the electromagnetism. So they're so the photons, they're the force carriers for the EM forces. And we have cosmic rays, so these charged particles, so they are in the strong force region. And we have neutrinos, so neutrinos are mostly weakly interactive, so they are in this, you see the weak carrier is W boson and Z boson. And then you also, of course, have gravitational wave. So this is led by LIGO experiment. So this is in this gravity mass region. So the idea of using Martin messenger to study astronomy is, I think, something remarkable in this century. So we can not just using the EM particles, but also include all these different force, different interactions, and look at the universe in all this different perspective. So very brief history of neutrinos. So in 1927, there was an experiment, a beta decay experiment. At the time, it was expected it's a 2-body decay, very simple. So when you look at the electron, you expect the distribution to be almost a delta function. But in reality, when they look at the electron energy distribution, they see actually a very wide distribution. So at the time, it was thought the 2 explanations, most popular was the energy does not conserve. So a lot of people were working on that area. And Wolfgang Pauli proposed we're missing some particle in this equation. Like it's not 2-body, but there's something else. And he admitted at the time that he had done a terrible thing. He postulated a particle that can never be detected. So it was at the time already known that it's almost impossible to detect this particle. So in 1932, Chadwick discovered the actual neutron, because Pauli at the time was calling it neutron. So Chadwick discovered this neutral particle about the same mass as proton, so he named it neutron. And 1933, Fermi renamed this Pauli's neutron neutrino as audience must know, in Italian it means little neutron. So that was in 1933. The turn of the story happened in 1956. So that was by Rines and Cowan in a nuclear plant experiments for inverse beta decay. So there they were measuring the cross-section of this anti-electron neutrino, and they concluded, so this was a famous telegram that was sent to Pauli himself. So here they said, you need a slab of lead of about 10 to the 12 meters, so about 1 light years of lead to scatter 1 GeV neutrino at 50% neutrons. So you see it's extremely difficult to actually let these neutrinos to interact. So this observation was by indirect measurements of neutrinos. So this was the discovery of neutrinos. As today, as time moves on, we understand a lot better. So this is the neutrino, the flux distribution. So you see x-axis is energy here. Oh, so sorry, this is the cross-section. So that just means how easily this neutrino is going to interact. So at lower energies, you see there's the solar neutrinos at about MeV range, and then you have nuclear reactors here, you have supernova, dying stars, and you have accelerator here. So yeah, human technology can reach about here as today. And then you have atmospheric neutrinos. So these are the high energy cosmic ray charged particles interact with atmosphere, creating secondary neutrinos in these hadronic interactions, and then the weak interactions. At the highest energies, however, these are the neutrinos that could come from cosmic. So they are neutrinos directly from the source, for instance, from a supermassive black hole, or from all this type of very extreme environments that we can think of. So before IceCube was turned on, we did not really know if this cosmic component existed. We measured up to atmospheric, and after IceCube turned on, IceCube discovered this new species of neutrinos, which come from actually the universe outside of galaxy. So you see the interaction cross-sections, the probability of interacting increases as energy. And there's a very strange structure here. It's a resonance, which we're going to go a little bit further in the later stage of this talk. So the IceCube collaboration is a very international collaboration. We're mostly driven by the US, funded by the National Science Foundation in NSF. And also we have a lot of participants from Europe, so especially from Germany region. And we have Japan, Asia, Australia, New Zealand. So to go to South Pole, we will have to go to New Zealand, Christchurch, and go down to Antarctica by the airplane. So yeah, it's a very exciting collaboration. Our experiment is located exactly at the South Pole. So this is IceCube lab on the surface. So what we did was to drill holes down to all the way 3,000 meters, and we drilled 86 of these holes. So in each hole, we would then bury our light sensors to detect very faint light that created from neutrino interaction. So you see this is size of Eiffel Tower. Our experiment is much larger. Although on the surface, when you go to South Pole, you don't see them because they're beneath you. So each flag here corresponds to the position of a string, and there's 2 guardian angels here. So these are the surface detectors called IceTop. So they're much smaller. So they're used to study cosmic rays. And background here, you see there's some other experiments actually operating at the South Pole as well. So this is a picture. This is a movie of drilling. So to drill holes, you imagine at South Pole of 3,000 meters is very challenging. So we have this hot water driller, and you basically deploy this very heavy machineries to the pole, and then because in the summer there's no night, it's always daylight, so you can work on 2 shifts. You have a team drilling in the morning and team drilling in the midnight. So this is how it was done. It was very difficult to make it work. So this is one of the digital optical modules, so PMTs buried inside of the IceCube. So you see we have more than 5,000 of them, in the ice, and you see this is how the detector then goes up to the surface, and this is IceCube lab. Right, so the deployment to make this holes and to put the optical sensors inside the experiment took a while. So you see we started from 2007 and completed about 2010, 2011. So this plot just shows you the rate of triggering. So on the y-axis is in hertz. So usually our trigger rate is about 2.5 kHz. So that means per second we measure 2,500 events. So the detection uptime is about 99%. Actually above that, we have 2 people live at South Pole, and so they are there 24/7 measuring this data. And you see this periodical rate. I'm going to introduce this later in the talk as well. So how the event looks like in IceCube when there's neutrino events going on. So you know, there's 3 flavors of neutrinos: the muon neutrino, electron neutrino, and tau neutrino. This is so when you have a muon neutrino charge interaction, you will result in a track here, and so this is how the photons then would scatter around in the ice, and this is how it looks like in our detector. So this is simulation, how the actually photon ray tracing will go, and this is the response function in the end in our detector. So this is cascade. It could be a neutral current of all flavors or electron neutrino of charged currents. And this is a tau neutrino. You have first the bound from the hadron from the charged current tau, and then you have a tau decay after the tau travels some distance with decay. So this is why you see 2 bound structure of the tau. So this is basically what we are trying to catch in our detector. So the detection mechanism is something called tranquil radiation. But that's when you have a charged particle going through the ice with speed larger than the speed of photon in the medium. It would yield this tranquil radiation. So it's really illustrated here. You see this is the trajectory of the charged particle, and you have this front, and you yield this the strength of usually in the UV range of photons at this cone, as you saw in this video. So you see a cone of light just following behind the charged particle. So charged particles were created from neutrino interactions. Neutrino interact with ice and generate a bunch of secondary charged particles. Okay, so you saw this earlier. So this is how IceCube looks like. And so these are some pictures during deployment. So you have this guy just after deploying a string, and he's standing actually on the support structure. You see he's actually protected here. And these are some pictures of the optical modules we have just in the lab. We put all of them now. They're all living beneath the beneath the ice. So this is how it looks like when you drill the holes. And this is people laying out these cables outside the hole all the way to the IceCube lab. So this is to put things into perspective. So people live at the South Pole Station. So there are about 50 people live there during the winter. And this is IceCube lab. So you see each dot here corresponds to the position of the string. So one day, if you ever go to South Pole, you'll probably walk past one of the IceCube strings. So this is the BESS experiment and the South Pole telescope also operating at the South Pole. What we do is we take data, as you remember, about 2,500 events per second. We transmit this data to the surface, and then these events would reach the IceCube lab, ICL, and ICL, the lab would then distribute the events on the satellites, and then the satellite would then just send the events across the globe to everywhere on the planets. Okay, so it is a very complicated process, and we have a lot of people, technical people, working on this aspect. So it's a very collaborative project. A very simple history. So we submitted a proposal in 1999. As you heard, our completion of the experiment is about 2010, so it's more than 10 years in operation now. We have already discovered the astrophysical neutrinos in 2013. So it's like we turned on the detector, immediately we saw there's signal. And then we discovered, so there's more discoveries here, and in 2018, we saw this first possible cosmic ray source called Texas 0506056. So this is a blazar. So this is an AGN that was a jet pointing at us. So this was done with the Mars Messenger campaign together with a Fermi telescope. Gamma ray telescope was flaring at the time when we saw this high energy neutrino. So the science we cover in IceCube is extremely broad. So we do astrophysics, of course, and we also do neutrino physics, measure neutrino oscillations, stereo neutrinos, neutrino decays, for instance. We also do Earth science, and we do dark matter search, beyond standard model search, and some fundamental symmetries. So we have people in all these frontiers, although our main focus is in this blue region, the cosmic ray, the astrophysics perspective of IceCube. So we see some of the events, a lot of the events we measure through the Earth. So this is an illustration. It's actually using the real data. It's a data visualization. So IceCube is, in the South Pole in the down here, and we measure these neutrinos going through the Earth. So this is actually a very nice app. You can find out where the neutrinos went through. Maybe you can find one in your hometown. So we have been tracking these events, and then we just, they must be neutrinos because they go through the Earth. So we actually then measured, so this is the diffuse flux, as x-axis is energy of neutrino, y-axis is the flux. So you see at its highest energies of 100 TeV, 10 to the 5 GeV, your signal, astrophysical, is much higher, start to dominate over the background. So that's an atmospheric neutrino. So this is why we say IceCube has discovered neutrinos from outside of galaxy. So this is very significant now. We could also, of course, use this through-going neutrinos to study Earth tomography. So you can study Earth core, for instance, and you can also study neutrino interaction cross-section, beyond standard model, etc. Some of the events come from all the way galaxies far behind, far away. So for instance, this is a publication we did last year. There's an object called NGC 1068, Starburst galaxy. So we saw at 2.9 sigma, the hottest spot in the northern sky is only 0.35 degree away from the source. Now, actually, we have improved the data, and the publication, hopefully it's going to come this year, is going to be truly exciting about the source. I think this is something we're very looking forward to. We're going to start to observe probably sources of neutrinos one by one in the years to come. So per second, I mentioned we measure 2,000 events. So most of the events actually are cosmic rays. So you see this color here actually shows temperature of the South Pole atmosphere. So hot means it's red, and purple is cold. So you see in each summer, we measure more events than in winter. So these are not neutrinos mostly. So these are muons from cosmic rays. And we understand why they correlate with the atmospheric temperature. So actually, we can use this to study the South Pole atmospheric environment. So this is, I think, something that's fun to bring up. So neutrino astronomy started, to be honest, because IceCube turned on. So so for instance, when we detect a high energy neutrino, we send it to this IceCube lab at South Pole, and it distributes over the satellite. So delay is about only 33 seconds at median, and then it sends to different partners, for instance, the gamma ray observatories, X-ray, optical, gravitational wave. So we've done several of this exercise to follow up high energy neutrinos from IceCube, try to detect the partners. So this is one of the most famous events called IC 1709228. So it happened in 2017. So this is where the event is. So this is a galaxy. So you see the event was outside of galaxy, actually from a distance 5.7 billion light years away. So this was detected because was flagged because there was at the gamma ray experiments, they saw a flare in the gamma ray at the same time as neutrino. So this was about 3.5 sigma significance level, but this ultimately shows us what in principle multi-messenger astronomy can do, and the potential in the future for us to detect more sources. This is a very recent publication in Nature we just published a few months ago. So this is about a detection of electron antineutrino. So antimatter was discovered firstly by Carl Anderson in 1932. So there's a picture of cloud chamber operating magnetic field. So you can work out from the curvature of the trajectory of the charged particle that the particle that Anderson saw at the time must have the charge similar with an electron, but it's positively charged, and with the mass, so charge over mass ratio similarly with the electron. So that was a positron today we know of, but at the time it was very skeptical of what was going on. Today, so this is a picture of this event of electron antineutrino, where the W boson resonance, or also called Glashow resonance. So that is when you create on-shell W boson at 6.3 PeV, and the W boson will decay to a hadronic shell, and you see as this cluster events that we saw. So this was only possible actually to be detected by IceCube-like experiments because energy here is just too high for accelerators, so we saw earlier. So only nature at this point can provide us such a test for standard model, because W boson was predicted, excuse me, well in the standard model, but it was never observed this resonance, and this is the very first time that we're able to see it. And it's just not possible before because human accelerators will not be able to reach this energy. So that's something that was super exciting. So if you look at the physics plot, so x-axis here is the energy. So this is the new event. So we're able to extend IceCube previous measurements to higher energy at 6 PeV. And all this, you see these arrows here are the upper limits. So we haven't actually discovered any neutrinos above this energy. So they're all upper limits. But this is what we want to do next with next generation Gen 2. So yeah, if you are looking for PhD projects, actually IceCube Gen 2 could be something very interesting for you because it is going to be built. And we are looking at the energies beyond at 10 PeVs or cosmogenic, even highest energies to make more discoveries, for instance, to look at the highest energy phenomena at the universe. So this is orange is a measurement from the POG Observatory of cosmic rays, as you see, and you see the actually the power of IceCube neutrinos is at very similar power as the ultra high energy cosmic rays. So usually this means these two components could be originated from the same source. So it could be that there are a lot of models predicting IceCube connection linked to the sources of ultra high energy cosmic rays. So we're really hoping that we'll be able to resolve that mystery as well, where the ultra high energy cosmic rays comes from with the neutral particle neutrinos. Yeah, so this is very exciting. So in the end, I'm just going to show you a few pictures. So this was in the Christchurch in New Zealand before we boarded to the Antarctica. So it's where the US military planes, and you see this is some of the pictures that I took above the sky, and you see this ice melting. And so this is the McMurdo. So this is already in Antarctica. This is their airport. And I saw just one single penguin walking around. I didn't see any other penguins, unfortunately, in this trip. So this is the bus that's operating in Antarctica. You see, with huge wheels. It looks very different. Yeah, but this is basically the life. And if you live there, and this is how it looks like when you fly above Antarctica. It's really beautiful. So these are some lakes, but of course there's frozen. It's truly a remarkable experience, and you see the different types of planes flying around. One thing I would like to bring to your attention is South Pole is not just cold, as you know, it was that day. It's very windy. Air pressure also is a problem. So IceCube, it's 2,000. So we drilled the holes 3,000 beneath ice. That's because IceCube is actually very tall. It's very high on altitude. It's at 2,000 something meters. It's almost 3,000 meters. So you're literally standing on a mountain. So the air pressure is very thin, and also because how the Earth's rotation goes, the equivalent, the altitude is about 3,000. So you're operating in very thin air, in the very cold weather, and it's very dry. It's actually Antarctica has the largest desert on the Earth, so it's really in a very tough environment. So you see these are some plants that planted in the South Pole Station. So this is from a greenhouse, and this is how the dormitory looks like. I was lucky to have some decoration on the wall, and this is just some ceremonial pole and also the flags of the countries that's operating in that area. And yeah, so we did some installation of new experiments, radio experiments, and you can see this. Occasionally we see something called sun dog. So it's a very beautiful phenomena that you found at the South Pole. And this is a data center at the IceCube lab. This is IceCube lab and how we distribute the signals around to the satellite. And you see this something called white desert because it's so dry. So the ice, yes, you look at everything, it's like sand. It's not like ice that you know of, we know of in the normal setting. So it's very interesting. Okay, so in the end, I would like to advertise this augmented reality app that actually I helped to write. So it's called IceBear. You can just search IceCube AR in the Google Android or iOS, and then you will be able to see a hologram IceCube event and also where they come from in this app. So if you're interested, you can either talk to me afterwards, or you can just search. There's an article about this augmented reality app, and then you can receive real-time IceCube alerts via this app as well. You can see when the neutrino comes, you immediately get a notification. You can see how it looks like. So the conclusion is IceCube has been in operation for over a decade with more than 99% of uptime, so it's very successful. We discovered diffuse neutrino flux. We started neutrino astronomy. We have seen the first hint of tau neutrino, Doppler boson, Glashow resonance. We've seen the transient source, possibly, and also steady source. Yeah, so that's the end of the talk. Thank you very much.
So thanks a lot for the very nice talk that you had. So I don't know if there are questions from the audience or just curiosities about the talk. Marco, maybe you can read if there are questions in Teams, because
so far people have been shy, so don't be shy. Write your questions in the Teams chat, or if you're on WebEx, you can also raise your hand, activate your microphone, and ask your questions.
But in the meantime, I have a question, just a curiosity. How many times did you spend in IceCube lab?
Oh, I only have been there once. Stayed about a month.
A month. Okay, so it was in summer, no? Because during winter you cannot travel there, if I'm right.
Yeah, exactly. So I went there about December, so just after Christmas.
Yeah, it's South Pole, so they say the season are inverted. Just. I think is a very nice experience. It's some place where you cannot travel. You can go in vacation there.
Yes.
The only way is to join such an experience.
Yeah, you have. Actually, you can be a tourist. So I saw some tourists, which is really funny. But so Antarctica is a very special continent. So there's a treaty that people only go there for science reasons. So you cannot pollute the continent, and you go there, everyone is peaceful, just do science. So it's a really special feeling over there.
So if I may also have a very naive curiosity, for us not working in astrophysics or astroparticle physics, Me personally, you know, I tend not to understand the difference between some of the experiments that are going on about neutrinos. So, for example, I know we have a, you know, the Gran Sasso lab here, very close to where we are. So it's actually a question for both of you and Francesco, if you want to answer. What's the difference between, you know, the key differences between the IceCube experiment and the Borexino or the other experiments going on here at the Gran Sasso lab?
Francesco, please feel free.
No, okay, is a matter of energy. If you see this plot from Lou that is here, you will see that experiments like, for example, Borexino are listed here, where the energy is lower than the highest part where IceCube is investigated. So basically, it's a matter of the source that is producing the particle, the neutrino, and also it's a very different thing because if you produce these neutrinos at highest energies, then you should have a mechanism to produce them. So it's more difficult to produce particles at the highest energy. So let's say the source is different. The technique that you use, the source of the particle is different. The energy of the particle is different, and then the technique that you need to detect is different. Then in Gran Sasso you have also other experiments that treat neutrino, but are of different. Is a different topic. But in general, it's the energy, I think, that is differentiating the experiment of Gran Sasso with respect to this one.
Yeah, I agree. It's almost like from X-ray to gamma ray for photons, if you're more familiar with that.
Yeah.
So in other words, let's say the IceCube experiment is able to study, you know, neutrinos with higher energy, which originate further away into the space, whereas maybe the Borexino is able to detect ones that are originated closer. But so is there a difference in sort of sensitivity of detection? Like, for example, is there a trade-off where IceCube can detect neutrinos that are further away but not with the same efficiency, or is it just?
So it's more to the energy. So for instance, so at these energies you're looking at supernova. The supernova are the dying stars. We have a lot of supernovas in our galaxy, about 2 of them per century. But what IceCube, so this is the experiment you're familiar with, but IceCube we're trying to measure is like, I don't know, 7 orders of magnitude higher. Sorry, that's nonsense. But it is much, it's much higher energy, and it's probing the highest energies. So we understand the physics of supernova, I think, fairly well. Not to the like 100%, but we're more comfortable with this. By the highest energies, you can imagine how hard it is to accelerate particles to 10 to 20 electron volts. So for PLG, for instance, if you accelerate charged particle proton to PLG energy, then you need to build an accelerator Large Hadron Collider here with the radius from the Sun to the Mercury planet. So it's just so enormous, and it's very hard to understand how the universe does this. And this is why we need this highest energy experiments in order to probe this really the most difficult questions. Yeah, if you're interested in supernova, then you're fine with these experiments. But IceCube is built for much higher energy.
Yeah, that's fascinating. Thank you both for your answers. I think there is Giovanni who is trying to ask a question. Let's see if he's going to write it or come onto WebEx.
I put my question in the chat.
I see the question. Okay, from Giovanni. The question is how long it takes to measure the neutrinos from the time they touch the sensor to the time it is recorded in the computer?
Oh, it's about nanoseconds. Or sensor. So I didn't put any technical plot here. So these optical modules are able to have resolution on about 2 nanoseconds. Yeah. So yeah, so this electronics were done very, very nicely.
Yeah, if you can give also an idea how much, how long in time is such an event, for example, in the detector?
Oh yeah, it's a great question because it depends on what you look at. So if you look at tranquil, just tranquil, we're at microseconds level. But if you look at, you're measuring hadronic shower, so there's also neutron decay, like, then if you look at the particle part, it could last for seconds. But at the moment, yeah, we will have to develop our readouts, like the data, especially to measure this neutron decays, which is something we're trying to do.
Okay, another question from Anna Maria Tetti is there any biological experiment running in relation to the physics ones to investigate the impact on life?
This is a very deep question. So I'm pretty ignorant on that, but I know 2 things. So one is I know the people that are trying to drill holes, collect the sample and try to analyze like bacteria at the South Pole because, it's a very clean environment. There's no human activity. And if you go deeper, the deeper you go to the ice, actually you go deeper to history, right? So I know there are people doing that, and we're in collaboration with them because we're interested in ice property to study neutrinos. And a second thing is, I think there is recently a publication on cosmic ray possible. Sorry, I probably shouldn't mention this. It's not related to neutrino, but I know people are hypothesizing the cosmic rays could have something to do with the origin of life. Maybe I can point you to the publication, but it's not related to IceCube.
Marco, I don't know if there are other questions.
I'm also checking on YouTube. Currently, there are no questions. Or no other questions.
People is shy.
Yeah, so I encourage you, if you're looking for projects, we have very rich physics, and we are going to go upgrade for Gen 2. We're also collecting collaborators for Gen 2 as well. So I think about
which is the type of upgrade that are you going to do?
So we have 2 stages. So phase 1 is, so this is the IceCube. So we are going to do an infill of, so inside. So only deploy 7 strings. So that is going to test a new type of sensors. So instead of this one, we have better R&D ones, and to study neutrino oscillations. So you see, it's a precision frontier. And then afterward, we have IceCube Gen 2, which is about 10 times size of IceCube. And that is in the R&D stage. We are currently working on to study.
So the first phase, is basically to go to lower energies.
Phase 1
and then the second phase is to extend the number of events that you can have at the highest energies. Because if you enlarge the area, no, I'm speaking because people in the audience are not familiar maybe with this. We are, but they are not familiar.
Sorry.
So if you enlarge the area, you will, as you have very few particles at the energy. If you enlarge the area, then you increase the number of particles that you can have, and this is to increase the number of particles at the highest energy. If you increase the number of detectors in a small area, then you are more sensitive to lower energies particles. So you can do a bridge between lower energy and highest energies.
Yeah. So one year of IceCube, 10 years of IceCube is about 1 year of Gen 2. So either you wait for 10 years of IceCube or you wait for 1 year of Gen 2.
But you need 5 years to build. So at the end, no, I don't know how many. So at the end, you gain in any case. And okay. Okay, I don't know if there are other questions. I don't know. Ah, okay, there is another one. Okay, Marco, go ahead, please, because I cannot read the.
I put them in the chat here on WebEx. I don't know if you can access.
Ah, okay. In the chat. Okay, there is how difficult it is to be recruited as a scientist in the IceCube lab.
So it depends on you're doing hardware or software, but I think we're open. So, so for instance, in UNIVAQ, IceCube Center at Madison. So Madison is the hub of IceCube, not at South Pole. So we have a lot of scientists. We usually have open positions. Yeah, I mean, if you're interested, you can drop me an email. So I'm currently assistant professor at UW Madison.
Okay, another question is there, from Giovanni, is there any public repository of the data collection software?
Yeah, it's a good question. So open data is something we care about a lot. So we have, so we're working on a GitHub. So to open our software, like we have GitHub open source, you can check out. And also we release our data regularly. So we recently released a 10-year IceCube point source catalog. So you can do your own search. You can look at your favorite source, whether there's anything going on there. Yeah, so we do.
Okay, so I think I read all the questions that are in the chat because one is repeated 2 times, I think. Okay, so if there are no other questions for Lou, I want to thank her for the kind invitation. I remember that we moved the meeting because for her otherwise was too early in US.
Thank you so much for that.
But I think no, I think it was worth for hearing about this fantastic experiment in Antarctic. And then I thank you again, and I wish you a good day.
We have a late breaking question on the.
Okay, go Marco, because I cannot read.
Okay, so from Simone Masci, about supernova explosions between gravitational waves detectors and neutrinos detectors, which of them is the fastest to discover that event and communicate it to the astronomers?
So there are different models. It depends. I think the question is whether there will be first neutrinos or first the gravitational waves, right? I think the most conventional hypothesis at this moment is you will first have the gravitational waves and neutrinos come after. But this is very open, I think. So this models were open. I don't think we have gravitational waves from supernova at this point. We haven't detected them, but most from colliding neutron stars.
But in any case, it's not a race. It's a
right.
I think the two information are complementary in the sense that they gave different informations, and so they are needed both. So there is no. It's not a race between the different experiments.
So, yeah, so neutrinos have the very special advantage that you can look into where the interaction happened. You can study exactly precisely where the acceleration happens. The gravitational wave is large. It's about the mass, the scale, right? The distance. But yeah, it's a complementary.
Okay. So again, Lou, thanks a lot for the talk, and I wish you a good day.
Thank you so much.
Bye bye.
Thanks. Bye.
Hello. Bye everybody.
Thank you.